Welcome back for our last discussion in Chapter 8. We're going to wrap up our techniques of integration by talking about our last technique, which is going to be partial fraction decomposition. And so if we kind of remind ourselves of the techniques we learned, there were 3 in this chapter. First was integration by parts, which was kind of like the product rule for integration. The second was kind of a trigonometric thing, right? It was a substitution technique that involved trigonometry. And in this case, it's kind of an algebra technique that's going to help us solve integrals, specifically fractions. And, fractions are already hard to deal with. And so if we can make the fractions a little bit easier on us, it might help us solve certain types of integrals. Now, just like any technique, it doesn't apply to all sorts of integrals, only specific scenarios. For example, integration by parts, we're looking for products in which I can't use u sub and we can get part of our answer every time we do it, right? We have to take the derivative of one and the antiderivative of the other, so we need to know something about each piece in the product. The trigonometric substitution relied on a certain type of algebraic expression, right? A sum or difference of squares, preferably under a root, in which we can use a certain trig function to transform that integral into a trigonometric integral that hopefully we can answer. And we spend a section talking about trigonometric integrals. And now what we're going to do is we're going to remind ourselves actually of a pre-calculus technique. We actually talk about this in pre-calculus, this idea of taking a fraction and splitting a fraction into a sum of smaller fractions, or what we call partial fraction decomposition. We're used to in algebra taking fractions and adding them together, creating a single fraction. And now we're trying to go the other way. We're taking a fraction and breaking it up into a sum of smaller pieces, sum of smaller fractions. Why would that be useful? We'll see when it comes to integration, but just like the last technique, we actually won't do any integration today. We're just going to get used to this idea of decomposition, just like we introduced the trigonometry behind trig sub. And then in the next video, we'll get to actually taking this technique, taking this pre-calc concept, this algebra concept, and applying it to integration, seeing how it will help us. And so the setup for partial fraction decomposition, of course, just like any setup, it requires a certain type of scenario that we're given. In this case, we have to be given a rational function. A rational function is a fraction, and actually it's not just even any fraction. So we have a function in a numerator, a function in a denominator, and they are both polynomials. So no roots, no trig, polynomial expressions. So powers of x, constants in front, sums and differences of those. And so polynomial. So a polynomial over another polynomial is what we call a rational function in math. And so we have to be given a rational function. A couple setup requirements. One is that fraction, that f of x, that rational function, better be proper. What do we mean by proper fraction? Think back to even grade school when you talked about fractions. A proper fraction means the denominator number is larger than the numerator number, like 3/4 or 5/8. 7/3 is not proper. It's not proper. The number in the numerator is larger than the denominator. And what do we mean by not proper is, remember, a fraction represents division. And since the number on top is larger, that means you can actually perform some sort of division. You can get a quotient. And so we want to make sure that our fraction is proper, that division can't be done. That the denominator, these are polynomials, that the degree of the denominator polynomial, right, the leading power of x, the power of that x, that the degree of the denominator polynomial is strictly larger than the degree of the numerator polynomial. And this inequality is strict, because if they actually were equal, you can actually do long division. And so if it's proper, we're in good shape. If it's not proper, we have to go back and remember how to do long division of polynomials back in algebra. Okay, you do that, long division of polynomials in algebra. So if not, you need to use long division to simplify it. So you'll get some sort of quotient out that you can pull out, and then a remaining fraction, your remainder fraction, if it doesn't divide evenly. And in that case, that fraction will be proper, and then we can proceed with the remainder fraction. And so we want to make sure our fraction is proper. And then d of x factors. What do I mean by that? The denominator, we can factor it in some way, right? It's a polynomial. So we can pull out some linear terms, you can factor it, maybe quadratic terms, depending on how large the polynomial is. And hopefully we can factor it completely. Right? Factor it as much as we can. It's going to be the goal. And so what we're going to do, and when we do partial fraction decomposition, is we're going to take a proper fraction, a proper rational function where the denominator factors. We will factor that denominator as much as we can. And then based on the factors that we get in the denominator, that will tell me how many terms I get in my decomposition, how many terms I can split it up into. So we're breaking up a fraction over the factors of the denominator. Now, technically, this is a technique that is talked about in pre-calculus. You actually do this in pre-calculus. So if you remember your pre-calc class, you may be having flashbacks of doing this back in pre-calc, but we're reminding ourselves of this in this section. And so what are we going to do for partial fraction decomposition? We're going to take a rational function. We will factor that denominator polynomial completely. What I mean is factor as much as you possibly can. Factor it up as much as you can until you can't anymore. Now, we can consider all sorts of scenarios for how the factorization looks. For our purposes, we're only going to be looking at linear and quadratic factors. So we're going to assume that we can factor the denominator, and when I do it, I'm either going to have a bunch of linear factors and worst case scenario, some quadratic factors that I can't factor anymore. And so we say we factor that polynomial completely in the denominator, and say I have some linear factors, some x minus a's, some linear factors, and say I have n of those factors. Because we know from algebra, when you factor polynomials, we get multiple factors, multiple of the same factor, like x minus 2 times x minus 2. That's x minus 2 squared. Or x plus 1 times x plus 1, x minus 1 squared, or x plus 1 squared. So you may get multiple of a linear factor. And so for every factor of the form x minus a to the n, so say you have n of these linear factors in that factorization, then you will get n terms in the decomposition when you split up the fraction into pieces. So for that power on that factor, that will give you n terms in the decomposition. You get one term for every power of that factor. So you'll split the fraction up into something over x minus a plus something over x minus a squared plus something over x minus a cubed plus something over x minus a to the n. Of course, if you only have one of those linear factors, then you get one term in your decomposition. If you have two of those linear factors, two terms in your decomposition, and so on. So for the power of the factor, you get that many terms. And that is consistent across the board, right? Even if you factor your polynomial and say you have some sort of quadratic factor, and say you can't factor this quadratic anymore, right, as far as you can factor it, and say for some reason you have n of these, so maybe there's multiple of the same quadratic factor, then you will get n terms again in your decomposition, one for every power of that factor. So those will be your denominators, those are fixed, and then you have some unknown numerators. In this case, a linear numerator, a 1 degree less numerator. So a1x plus b1, a2x plus b2, anx plus bn, where your ai's and bi's are just some unknown constants. Where the math comes in is you need to then find those constants. That's going to be actually the goal. Is as long as my fraction is proper and I can factor it, I'll know what my decomposition should look like based on this principle. I'll know how many terms I have in my decomposition. I'll know what the denominators of each of those terms are going to be. That's just given based on the factorization. What I do not know, what's unknown to me, is what the numerator should be in the decomposition. Whether they're just constants in the numerator or some unknown linear piece in the numerator, this is what we need to solve for, what we need to find. And so we're going to need to use some algebra, solve some equations, and figure out what those unknown constants need to be. And so we need to follow these rules. We can continue on. The pattern actually continues. If you have unknown cubic or, irreducible cubic factors, you'll get one for every power of that irreducible cubic that you have. And then in the numerator will be some unknown quadratic. Right? We'll continue on, but that would just be mean and very hard to keep going with. Yeah, and so these are the rules we need to follow. And so what we're going to do now is just kind of practice this. So we're not actually going to find these unknown constants. We'll just get used to the idea of how we're going to do the decomposition, how these rules work for us. So we'll go over here, and what we have is just a little practice, partial decomposition practice. And so what we're going to do, and I was nice in these cases, I gave you all proper fractions, so we don't have to worry about remembering how to do long division right now. And so they're proper, the degree of the bottom polynomial is larger than the numerator. And so they're proper, and they all factor. In the last case, I actually already factored it for you. But in these cases, we need to factor it. So we'll factor it out completely as much as we can. And once we factor it, that will determine how many terms I have in my decomposition, what the denominator should be, and then I have some unknown numerators that I'm going to need to solve for. And so if we look at the first example, it's proper, so let's go ahead and factor that denominator as much as we can. It's quadratic, so in this case, it's quite nice. It's going to factor into x plus 5 times x plus 3. Factors that multiply to give me 15 and add to give me 8. It doesn't reduce at all, so we're just left with this. And then what that means is, okay, we look at our decomposition. We have two linear factors, each of power 1, right? There's only one x plus 5. There's only one x plus 3. And so I get one term for the x plus 5. I get one term for the x plus 3. The numerators are some unknown constants. I can call them A1 and A2, but I'll just do A and B since we have 2. So unknown numerators, right? So for every power of this factor, we get a term. There's only one of them. So I get one term for the x plus 5. We get one term for the x plus 3. Give me a total of 2 terms in the decomposition. I know how many terms I have. I know what the denominators are going to be. I just don't know these numerators. They are unknown constants that we're going to need to find and solve for. So let's do the other one. Let's just get practicing using this idea of decomposition, how it works. So in this case, I'm going to, again, factor the denominator polynomial. In this case, I'm going to factor out an x squared, leaving with x squared times x plus 2. Now it is factored completely. I have two linear factors. I have x plus 2 and x. Think of x as like x plus or minus 0, right? X minus 0 is just x. That's a linear factor. But in this case, I have two of those factors, x squared. So I have a linear factor squared, x squared. And so in that case, that gives me 2 terms in my decomposition. I get one term from this factor, so a total of 3 terms in my decomposition. One for every power of x that I have. So I have x to the 1, I have x squared. That's for this. And again, the reason it's 2 terms, again, it's not quadratic, this is linear. We're thinking of this as x minus 0 squared, right? That's just x. We don't write that. You just write x squared, but that's a linear factor, x minus 0, that's squared. So I have 2 terms for that factor, and then I have 1 term for this factor. There's only one x plus 2. And so in total, I have 3 terms. 2 terms from this factor, 1 term from this factor. I get 1 for every power. So for example, if this was x cubed, I would have x squared, and x cubed. So I would get 3 terms from this factor and 1 term from this one. Again, the numerators are general unknown constants, b and c. And so again, let's go to the last one. This case, I already factored it for you. So let's just walk through how this is going to work. If I look at the factorization, I have x minus 1. Now I have 2 of those x minus 1s. So that means I get 2 terms in the decomposition from this one. One with x minus 1, the other with x minus 1 squared. The next factor is an x plus 2. I only have 1 of those, so I get 1 term for that guy. X squared plus 1, that is a quadratic, but I can't factor it anymore. It would go into imaginary numbers, which we don't do. And so x squared plus 1 is an irreducible quadratic, and so I only have 1 of those quadratics, so I get 1 term for the x squared plus 1. And then we have the appropriate numerators. Here, the linear factors just have some unknown constants, a, b, and c. The quadratic factor has an unknown numerator as well, but it is an unknown linear factor, so dx plus e, say. D and e are unknown. And so in these cases, right, given these rational functions, these are how they would decompose. The first one decomposes into 2 pieces, the second one into 3 pieces, and the third one into, in this case, 4 pieces. And so I'm just, in this case, following the rules of decomposition. I make sure it's proper, I factor completely, and then for every power of the factor that I have, I get a term in my decomposition. So that's why, again, in this one, we had 2 terms from the x squared. You get 2 terms from the x minus 1 squared, 1 for every power of that factor, up into n. In this case, 2, in both cases. And so that's how the decomposition works. That's just following the rules. So I'm not doing actually any math necessarily. I'm just factoring a polynomial and following the structure. Now comes the algebra. Now comes the actual math part, because now I need to find these unknown numerators. I need to solve for A, B, and C, and D, and E. And so let's look at we'll do the first two. This one was just to kind of illustrate this. This is more practical and something you might see. Let's actually find what these A and B are. So remember, we took x plus 2 over x squared plus 8x plus 5, and we're going to, or plus 15. And we know it can decompose into something over x plus 5 plus something over x plus 3. Now, what are those somethings? What is A and B? Those are what we need to find. So we need to solve for A and B. Now, anytime you're in algebra and you have a fraction, the first thing you learn in algebra when you deal with fractions is you like to clear fractions. How do we clear fractions in math? We multiply a whole equation, right? This is an equation. We can multiply a whole equation by anything we want. What I want to multiply by is the denominator. If I multiply this whole equation by the denominator that I started with, then all my fractions will be gone. Why? Because, well, if I multiply through by the denominator, which is this, on one side it's gone, and on the other side we have a factor that would cancel in each case, leaving me with no denominators left. So what I'm going to do is I'm going to multiply this whole expression by x plus 5 times x plus 3, right? The factored form of my denominator, this guy. Why do I want the factored form? Well, because I want to see what cancels in these terms. On the left-hand side, when I multiply through, the whole denominator is gone, leaving me with only x plus 2, the numerator. On the right-hand side, when I multiply to the first term, the x plus 5 cancel, leaving me with a times x plus 3. When I multiply into the second term, the x plus 3's cancel, leaving me with b times x plus 5. And now we need to solve for A and B, right? So I've just taken my expression, the decomposition I've written out, and I need to find A and B, so I've cleared my fractions first by multiplying through by the denominator. Specifically, again, the factored form of the denominator. That way you can see what cancels in every term, giving me this. Now again, we want to solve for A and B. If you look at this equation, there are actually 3 unknowns here: A, B, and x. Since I only care about finding A and B, x becomes what we call in math a free variable. It's a free choice. I don't need it to be anything arbitrary. I can make it specific. Who cares what x is? I just want A and B. I want to solve for those unknowns. X is unknown in general, but if I replace x with a number, that's going to give me an equation A and B, and maybe I can solve for A or B. And so we call that in math again a free variable. X is free. It's irrelevant to what I want to solve for right now. So that means I can choose it to be whatever I want. Now, I'm going to make specific choices for x. At first, you might wonder why I want to make x be -3 or -5. Why don't I choose 0 or 1? And you could. You could choose x to be anything. The reason I choose -3 and 5 is because I'm looking at what I'm given in this expression. By making x -3, you notice that that would make this whole term disappear. It would be 0 here. And then I'd be able to solve for b. And if I make x -5, then this whole term is gone, allowing me to solve for a. Now we can't do both at once, right? We have to do one and then the other. So first, let's let x be -3. If x is -3, on this side we get -1, -3 plus 2. On the right-hand side, this term's gone because it's times 0. This term gives me 2b. -3 plus 5 is 2. Well, that means b is -1/2. I just found b. Well, let's do x is -5. If x is -5, then on this side we're left with -3. -5 plus 2. -5 plus 3, that's -2a. And the second term's gone, no b, right? -5 plus 5 is 0, 0b. Allowing me to find a. A in this case is +2/3, or I'm sorry, +3/2. So we just found a and b by letting x be whatever we want. And so what does that mean? That means that my decomposition is done. We found those unknown numerators, and now I know that this rational function can be split up into this sum of smaller pieces. Now, if you're in a pre-calculus class, you might want to, not leave this as a fraction of the numerator, bring the 2 down to the denominator and distribute it, make it look a little bit better. But for our purposes, it's actually going to be irrelevant to us, because when it comes to integrating something like this, constants can be pulled out, so I don't care. Right now, I'll just leave them like that. So we're able to decompose this fraction into, again, a sum of smaller fractions. So let's take the second one. Let's do that one. And so let's take 3 over x cubed plus 2x squared, which we know is going to break up into 3 pieces now, and find what those a, b, and c are. So I'm going to do the same kind of thing I did in the first case. I will take this and I'm going to multiply this whole equation for this decomposition by my denominator. Now I'm going to multiply again by the factored form of my denominator, so I know what cancels each time. So I'm going to multiply everything by x squared times x plus 2, which is the same as x cubed plus 2x squared. So on the left-hand side, the denominators cancel completely, leaving me with only the numerator, in this case, 3. On the right-hand side, I multiply by the factored form, so now I see what cancels each time. When I multiply the first term, 1x cancels, leaving me with ax times x plus 2. When I multiply the second term, all of x squared cancels, leaving me with bn times x plus 2 then. And the last one, when I distribute, the x plus 2's cancel, leaving me with cx squared. So I've taken this decomposition, I've just rewritten it by clearing my fractions, therefore allowing me, hopefully, to solve for a, b, and c in a little bit easier of a fashion. So if I want to solve for a, b, and c again, I'm going to do the same thing I did before. I'm going to realize that x is free, that I only care about a, b, and c, and x can be then anything I want. And so specifically, I'm going to choose x to be 0 and x to be -2 and see what that's going to give me. Why 0, -2? Because if I make x 0, then a and c are gone. If I make x -2, then a and b are gone. It's going to make my life a little easier. On the other side of the equation, it's 3. It's constant, so it's just always going to be there. So when I let x be 0, we get 3 equals gone, 2b, gone. And so that means b is 2/3. Or sorry, again, 3/2. When x is -2, well, on the left it's 3, it's constant, equals gone, gone, -2 squared is 4, so 4c. So c is 3/4. 3/4. And at this point, you're like, okay, well, how are we going to find a? How am I going to find a? I know b, I know c. I can't choose another like 0 or -2 because both 0 and -2 will make a go away. So I need to pick something that won't make a go away. And unfortunately, that means whatever you pick, b and c are also going to still be around. Remember, x is still free, so you're going to choose it to be something. For example, I'm going to choose x to be, let's just do 1. When x is 1, let's see what we get. We're going to get 3, of course, on this side, equals, when x is 1, 1 plus 2 is 3, times 1 is 3, so 3a, plus, when x is 1, that's 3b, and when x is 1 plus c. You're like, well, still, that's hard, because how am I going to solve for a? I have b and c here. Well, remember, you just told me what b and c are. Don't forget the work that you've already done. That means that this equation can be simplified. B is 3/2. We solved that a second ago. C is 3/4. We solved that a second ago. Now the only unknown is a, and we can solve for it. We have to combine some fractions, but we can do it. So 3 plus 3a plus, we get 9/2. Oh, 3 equals, sorry. 3a plus 9/2 plus 3/4. So let's make everything into fourths. So 12/4 on one side, I'll subtract that in terms of fourths, so minus 18 fourths. Right? That'll be 18 fourths. And then this minus then 3 fourths to the other side. That's going to equal 3a. So what do we get? We get 12 minus 18, negative 30 fourths. Right? 12, or sorry, positive 12 minus 18, minus 8, not negative 12. 12 minus 18 is negative 6. Negative 6 minus 3 is negative 9. So we're going to get negative 9 fourths equals 3a. Dividing both sides by 3, the 3 and the 9 will reduce, and we get a is negative 3/4. So we have our 3 unknown numerators, a, b, and c. Now we're not done, right? I mean, we just found those unknown constants. That doesn't mean we have the decomposition. We have to, of course, write the decomposition. But now that we know the unknown constants, we can fill in what we have. So that means going back up here, I'll just erase a, b, and c and fill them in with what we just found. A was negative 3/4. B was 3/2. And C was 3/4. And so we were able to do this decomposition, find those missing constants, and now we know that we can take this expression and break it up into the sum of smaller pieces, these smaller pieces. Why do we care to do this, right? At no point have we talked about anything about calculus at this point, and that's what the next video is going to address, is why do I care to do this? Well, say we had to take the antiderivative of this function. Well, if I want to take the antiderivative of this rational function, not easy. In fact, U substitution doesn't work. Partial fraction or integration by parts, nah, I wouldn't know how to do that. Trig sub, it's not a sum or difference of squares. Maybe you can make it that by completing a square of a quadratic or something. Not fun. So trig sub kind of out unless I want to do a lot of algebra work. But hey, if I can decompose it, look at what I can break it up into. Integrals break up over sums and differences, meaning as long as I know how to integrate this, which I do, you got ln in Calc 1, and as long as I know how to integrate this, which I do again, we can get an answer. And so I can answer it. Same thing here. Integrating this, I have no idea. Taking the antiderivative, no U sub, I wouldn't know how to do integration by parts. Trig sub is not sum or difference of squares. It's a cubic polynomial. But if I break it up into these 3 pieces, I know how to integrate this, I know how to integrate this, and I know how to integrate this. Integrals break up over sums, and so I can get my answer. And so where this comes up with integration is it allows us a way to integrate rational functions that maybe I couldn't have before. That if I can maybe decompose it, I can now get an answer. By breaking it up into smaller fractions, maybe I know how to integrate those smaller pieces. And so that's what we'll do in the next video. We'll take this and apply it to integration.